in electrical device, there is two kinds of components. First of all, there is passive components like resistors, inductors, and capacitors. And there is a active component, which is consisted with those three passive components in like transistors, rectifier using a diode. So in these semesters, we're gonna concentrate on these active components. The transistors means that the sum of the word trans and resistors, which means it can vary uh, resistance with electricity, which means a electrical switch. For example, like MOSFET, metal oxide semiconductor field effect transistors, and bipolar junction transistors. Usually, we use wires to connect between passive or active components, but in this way, there is a excess resistance or the integrity of the circuits as is bad. So we started using a printed circuit board, and then nowadays we integrate it more by using a uh, uh, composing in systems on one chip. To interpret the chips or electrical device, we need two tools like physics. First of all, there is a Maxwell equations. The first equation of in Maxwell equations means that electrical flux passing through this closed space means equals to total charge in space. And the second is that sum of our magnetic flux in closed space is equals to 0, which means the uh, magnetic field or magnetic field, there is no magnetic monopole. And third, the difference of the electric field causes the change in magnetic flux. The direction of magnetic flux is orthogonal to electric field. And lastly, there is the current, and changes in electrical field causes the change of magnetic flux. For example, if the current flows like here, then the magnetic flux would be circling through the current. And there is another physics in microscale, which means quantum mechanics. There is two important properties in microscales, which is a wave particle dualities and the electron fermions like electrons has a quantized energy, which means the energies can be allowed at certain discrete level. So to represent these levels, we use these Schrodinger's equations like eigenfunctions and wave functions called psi. The absolute value of square psi means that electrons probability density functions of existence. And there is another properties that if potential barrier is thin enough, then the electrons can pass through the barriers. We call it the quantum tunneling. And there is a Moore's law, which means that the integrities of electrical device, which means number of transistors in IC, doubles every almost 2 years. To understand the mechanism in the semiconductors, we have to look about the atom structures. First of all, the electrons are orbiting near the atom nucleus. So if there is a one hydrogen atoms, there is a one electrons. Also, there is a one orbital, and electrons can exist in two states. And if there is two hydrogens, there will be two electrons and two orbitals and four states. And furthermore, if there is a lot of hydrogens uh, covalent bond, there will be n there is n number of hydrogens, and also there will be have two n states. So those atoms get bond each other, makes the band. So we can define two states. First, there is a conduction band, which means that the lowest level that electrons are fully empty at thermal equilibrium at 0 Kelvin. And there is valence band, which means that highest levels that electrons are fully occupied in thermal equilibrium. And the difference between the conduction band and valence band can be defined called a energy gap, energy band gap. In semiconductors, we use that the free electrons, which can be made with observing the energy from another systems or doping. If the semiconductors absorb the energies, then the electrons and hole pairs will be generated, which we call that excited electrons. And after some times passed, then the electron hole pairs will be recombined. By through these recombinations, the atoms will be emit the energy with the form of light or heat. And the atoms are aligned periodically, then we can use this concept, which is that spatial frequency with using these Fourier transforms. And there's another properties, which is the indirect band gap or direct band gap. The indirect band gap is that the valence band and conduction band are not aligned with same spatial frequencies, which causes the excess energies to emit energies or observing energies. However, these but their direct band gaps are aligned. Conduction band and valence bands are aligned together in same line, so that more efficient for emitting like optical devices. And using this band gap, we can define the materials that can be flow this current or not, or the middle part. If the band gap is large enough, then we call it the insulators. And if these metal, the band gaps, there is no band gaps, or if there is low enough, then we call it metals. So the metals have a equipotentials, and there's a lot of free electrons. Between them, there is a semiconductors, which are not big enough for the insulators. However, it's not close than the metal. And there is we can define the materials by the alignment between the atoms. The crystalline state is that there is a patterns like periodically aligned, and between them there is a polycrystallines. The polycrystallines are formed with the several grains, and the amorphous is not is completely not periodic. When we make semiconductors, we do not use intrinsic semiconductor because the intrinsic semiconductors has not enough free electrons or holes. So we use group 3 or group 5 material to make more free charge, free electrons or holes. We call it carriers. So if we dope group 3 materials, then the group 3 material accepts the electrons, so that makes the hole. We call these p-type semiconductors, and the atom which accepts electrons we call the acceptors. So the acceptors are ionized negatively, and if we dope with group 5 materials, then the group 5 materials donates the electrons, and also the atom that donated the electrons we call a donor, and the donors are charged with ionized with positively. The donor and acceptors are also known as a space charge. So using this doping technique, we can get a better carrier concentration or density. So that causes a good conductivity. Before that, there is a Fermi-Dirac distributions, which are the relationship between the energy levels or electrons concentrations related to the temperatures. The Fermi levels means that the probabilities that electrons exist 50% at 0 kelvins. Usually it's located at 0 Kelvin. It's located in a middle level in energy band gap, and there is a PN diode, which is a hetero structures using p-type and n-type semiconductors. At thermal equilibriums, the Fermi levels are constant. So we can determine that the acceptors levels or donors, how many acceptors or donors are doped. If the Fermi levels are close to the valence levels, the semiconductor is doped with p-type, and if close to the conduction levels, the semiconductor is n-type. And using these PN junctions or diode, we will bias it with the external voltage source or summits at the equilibriums, which when there is no energies put in from outer systems, then there is the PN junctions are shaped like here. The Fermi levels are constant, and there is a Boltzmann tail, which means that the electrons for Boltzmann tails means that the product between Fermi-Dirac distributions and density of states. So this Boltzmann tails means that the concentrations of electrons. and there is a slope, which means that there is a built-in voltage. So, and if we give the forward bias, apply a bias with forward uh, negative negative potential to the n-type and positive potential to the p-type, then the junction potentials would be get lowered so that the electron and holes can pass through these junctions. And if we bias it differently, positive bias to negative side and negative bias to p-type semiconductor, then the junction potential would be greater than the built-in potentials. And there is a diode characteristics. The IV curve. If there is no bias voltage applied, then the current will not flow. And if it negatively reverse bias the diode, then the current will not flow until the breakdown point. At breakdown point, the semiconductors can be break down because of the avalanche effect and the tunneling effect. And if we positively forward bias the PN junctions, then after the threshold voltage, then the current will be exponentially flow. Using these characteristics, we can use a diode in a solar cell photodiode and rectifier, because diode cannot flow through the at reverse bias. Also, there is a Zener diode which can be flow through both sides. And in solar cells, we use a depletion regions. In depletion regions, if the outer energies like heat or light, then the current are generated. MOSFET, which is a metal oxide semiconductor capacitance, is a capacitors using metal oxide and semiconductors. If we give a MOSFET on negative voltage and metal side, then by the attractive electrical force, the holes will be accumulated through oxide and substrate field surface here. And if we give a reverse bias, positive voltage to the metal side, then by the electrical repulsive force, then the holes would be drawn out to the ground side. That makes depletion area. And at that depletion mode, the total effective capacitance is the capacitance of oxide and depletion capacitance, the capacitance due to depletion. In depletion regions, there is no mobile carrier, so it affects to the total capacitance. And if we give more and more voltage to the metal side, then the minority carriers or electrons on p substrate would be accumulated. If we draw a energy band diagram, and it will be here. At inversions, the Boltzmann tail or electrons would be accumulated a oxide and substrate side, and in MOSFET, these electrons are used as channel. The MOSFET is similar to the MOSFET, but there is a source electrode and drain electrode. So MOSFET has 3 or 4 electrode, source, gate, and drain. And there is a body pin, a body electrode. Usually body electrodes are connected to a source. By inversions, MOSFET makes a channels to electrons travel through source, from source to drain. So it can function as an electrical switch through source and drain. The current and voltage characteristic of a MOSFET has 2 types. First of all, a ID, drain current and drain voltage, and drain current and gate voltage. So if we give a drain voltage through until threshold voltage, then the MOSFET acts as a resistive state, like we call it triode region. At some point, after some point, the threshold voltage, the current would be saturated. We call it saturated region. And if we look at the IDVG curve, before the gate bias, gate voltage is not over a threshold voltage, the current through the source to drain is very low. However, after the threshold voltage, the drain current would be increased exponentially. If we take a drain current log scale, then it'd be like here. So in here, by varying the gate voltage, then we can control this current flow, so using as switch. And the slope in the IDVG curve means that swing. The swing is that in depletion mode, there is 2 modes in MOSFET. First of all, a depletion mode. The depletion mode usually turned on. So the MOSFET uses the threshold voltages are here. And for the enhancement mode, it usually turned off so that the gate bias should be over the threshold voltage. Using the MOSFET, we can make amplifier and switch. Also, using for a logical device for memories or calculators, using a CMOS, the combination between FFET and MFET.